This is, John was asking me if like he would understand this lecture being kind of coming right toward the end of the class. But I think in many ways, this lecture of all the lectures in the class is relatively self-contained. It has one, and then undecidability, how there are some language that you can't write programs for at all. And we talked after that about reductions, about saying, okay, if this problem's really, really, really hard, and you can't decide it at all, then this problem would also be really, really hard, because I'm going to show you that if you could solve this second one, it would show a solution for this first one. And we know the first one's not possible, so that means the second one's not possible either. And that idea is called a reduction, reducing one problem to another by showing that the solution to the second would imply a solution to the first. And we did lots of examples of that. We turned problems about whether Turing machines can halt to problems about whether context-free languages, accepted the same grammar as another context-free language, whether accepted the same language as another context-free grammar. So we turned it into really practical questions. Somebody gives you two compilers. Do they do the same thing? There's no way to decide that. And that's because if there was a way to decide that, I could write an algorithm to tell you whether a Turing machine halted or not, whether a program infinite looped or not. So we did these reductions, but what we never did is I never really convinced you that there was ever even one original undecidable problem. I said if there was one, then this one would also be difficult, and this one would also be difficult. But we want to go back today and prove maybe the most fundamental result in the undecidability part of this class, which is that there really is one problem that you just can't do, and the proof of it is by this idea of diagonalization. It's this clever idea.
Yeah. Do you know what the program is? Trash. Whatever the program
No.
is.
Oh, are you doing it? You can just do it on the tape. Are you doing it on the computer at the same time?
That's what I was trying to do.
Don't try, because Sophia was warning me that it might not work. So if you just do it on the tape, you're okay. And then she will render it later.
Although I can't really see it.
You have to stand up the whole time.
Oh, I see. I see. But you have to look in.
I really plan on looking.
So just aim it more or less at me. Don't worry.
I do have a really good close-up of your beard right now. Can you tilt probably.
Get your drink. You got your own. Don't get tired.
Okay.
All right.
We're going.
Okay, we're going. We're live. All right. So the purpose of today is to show you that there really is an honest-to-goodness problem that you can never write an algorithm to solve. And I'm going to convince you of this in just a purely logical way. And it's an idea that started with a mathematician named Cantor back in the late 19th century, and then worked its way up through Alan Turing and Alonzo Church and all the people who did computer science stuff in the middle part of this last century. And then it results in this wonderful proof that there's no algorithm at all if I give you a program and an input for you to determine whether that program is actually going to stop and say, yes, I accept this input. Right? So that's the problem that I'm going to work on. It's called the halting problem. Again, here's the input to that problem. I give you a Turing machine or a program, and I give you an input along with it. And I ask you, is this Turing machine going to accept this input? Is it going to stop and say yes? Tell me, yes or no. All right, so that's the halting problem. The input is some Turing machine and a string that it's supposed to run on. And the output, yes or no, does M accept X? Does it stop and say yes? Now, if I asked you to go home and write an algorithm to do this, one obvious attempt would be to just take M, take the program, and run it. So you write a program that does nothing but read another program in, compile it, and execute it. You go borrow somebody's compiler and do it. You don't have to write the compiler yourself. Go ahead, take the machine in as input, take the input it's supposed to run on, and execute the program. And if it stops and says, I accept, then you say, yes, I know the answer. It stops and accepts. And if it doesn't stop and accept, then what do you do? Well, that's where you get in trouble with that method. That method's guaranteed to answer yes when it does accept x, but if the answer is no, if it doesn't accept x because it runs in some infinite loop, then your way of determining that will just be in an infinite loop. So maybe there's a more clever way to do it. Maybe you're supposed to really look at the program and start looking for funny for loops with weird initial conditions, that might not ever end. And after you do that, you can look for other strange things that might make the thing go into an infinite loop. And you categorize these into the 3,892 weird things that might make a program go into an infinite loop. And you write a 10,000-line program, and you send in your candidate machine into this program, and you check it for all the possible infinite loops, and none of them are going to cause any trouble. And then you'd say, I know this machine accepts x. I didn't even have to run it. I just checked it for no infinite loop. So I know sooner or later it's going to stop and say OK. That's a hypothetical. What we're going to do today is prove that there's no way to do that. There's no finite number of things that will let you check a program in general and make sure it will never go into an infinite loop. There's essentially an infinite number of ways a program can go into an infinite loop, and you don't have any way of being able to methodically check it in advance. Okay, and that's a very fundamental result. That means that there's a limit to what we can compute. There's a limit to what we can do. And it's not just this weird esoteric question, does a program run forever? Well, that's not too esoteric. I mean, that's kind of important. Does it run in an infinite loop? But then this ends up making all these other problems we really care about undecidable. Two grammars generating the same language, undecidable. That's a really important problem. In the book, Mike Sipser talks about a famous open problem talked about at the turn of the century, I guess 2 centuries ago, 1900, by David Hilbert. Hilbert gave a famous speech in Paris, which was based, Hilbert was the Renaissance mathematician of his day. Very well known, very renowned, and had his fingers in lots of different specialties, unlike the mathematicians of today who tend to be famous only in one narrow specialty, except for a very rare few. He really was the king of mathematics in his day. And he gave a speech at this turn of the century that basically said, look, here's 25 really important things that I'd like to know the answer to before the end of the next century. And it got a whole bunch of young and old mathematicians, churning their gears and working very, very hard. And I think it was 23 problems in his list or something like that. You can find this list on the internet. It's there. One of the things on the list was a method to answer questions like this. If I give you some arbitrary polynomial like this, does it have a solution where x is a whole number, where x is an integer? Now, you know how to actually solve that for linear equations and for quadratic equations. And there is a method for cubic equations, and there's a method for quadratic equations to actually get the exact solutions, and then you can just check if they're integers. But there is no general method, as far as anybody knew, for higher order equations. You would just do those numerically and get approximations. And he wanted to know, is there a procedure, some sort of algorithm, even though the word wasn't quite around in those days, but is there an algorithm for determining whether an equation like this has whole number solutions or not? Describe this procedure to me, and that will solve this problem. Now, Hilbert kind of implied that there is some procedure, you just have to work really hard to find it. The implication was that everybody thought that things like this were just computable. Anything mechanical you could do. It might be hard to find out how to do it. And then, many, many, many years later, it was proved, I think it was, oh gee, I forget the year, but it was way after 1950, I think. It was proved that this problem was undecidable. That there is no algorithm to do this. That there's no way, if I give you a polynomial and I ask you, does it have an integer solution, yes or no? Answer that. There's no algorithm to do it. You might be able to do it in a particular case, but not in general. So there's a real-life math problem that somebody really cared about to think that it was one of the top problems of the century. And not only didn't they come up with a solution, but the solution was completely unexpected. That there is no method. That's the answer to Hilbert's question. Not here's the method, but that no method exists. All right. So that's a mathematical kind of question that's undecidable, but there's many, many computer science questions that are undecidable. And we've talked about a lot of them. And many of them that relate to compilers, things that you just can't figure out and you just have to work on a case-by-case basis. All right, so this is all introduction. Other questions so far? Okay, good. How's it going, John, all right? Yeah. Okay, well, how are we going to show that the halting problem is really undecidable, that there's no way to do it? Well, here's a really bad way. I just get an infinite number of my friends, and I have them try every possible algorithm that might work, and when they all fail, I say, well, they all failed, so there's no way to do it. And that's no good, because I'll need another infinite collection to check all the other algorithms. There's a lot of algorithms out there, and you can't just check them all. So we have to have some kind of a reasoning, some kind of an argument that says no matter what argument, no matter what algorithm we try, it will fail to decide this question. And this idea needs the big guns of computational complexity, something called diagonalization. And I showed you this idea before in a simpler setting, and I'm going to show it to you again in a simpler setting, and then we're going to go back to this setting and use it. So take a minute, we're going to shift back to finite state machines for about 15 minutes, review this idea of diagonalization, bring it back up to this level, because the idea at this level will be just the same idea at the smaller level, but a little more subtle. All right, so get it at the basic level, and then the subtlety will be more clear. All right. Questions? Good? All right, so let's do this. Let's talk about finite state machines for a few minutes. You all know there's plenty of languages that are not acceptable by finite state machines. Here's one. 0 to the n, 1 to the n, right? We prove that this is not acceptable by any finite state machine, and we use some pumping lemma kind of proof to show it. Okay. But there's another kind of proof you can use to show that there are things that are not acceptable by finite state machines. We could bring the big guns of diagonalization out. And that's what I want to do now. And before I do it, we're just going to bring the big guns of diagonalization out onto that barber puzzle to make sure everybody remembers it one more time. Last time. There's a barber in town, and the barber shaves every one in town but me. That's right. Everyone in town who doesn't shave themselves. Seems like a completely reasonable thing to say. There's a barber in a town, and he shaves everyone in town who doesn't shave themselves. The barber lives in this town. There's only one town in the whole universe. The barber lives in this town. He shaves everybody in town who doesn't shave themselves. So, does the barber shave me?
I guess not.
I don't know. He's not doing a very good job if he was. If I shave myself every morning, then the barber doesn't shave me. And if I don't shave myself, then I go to the barber. It makes complete sense. But now the difficult thing is, who does a barber go to? If the barber goes to himself, then he shaves himself. But he's only supposed to shave people who don't shave themselves. So he can't really shave himself, because he's only supposed to shave people who don't shave themselves. But if he doesn't shave himself, then he's supposed to go to the barber. Everybody in town who doesn't shave himself is supposed to get shaved by the barber. So if he shaves himself, he's not supposed to shave himself. And if he doesn't shave himself, he is supposed to shave himself. This little conundrum, this little strange paradox, as simple and stupid as it may seem, because you could just talk about this in a bar when you're drunk and kind of go, oh yeah, well. But it's actually at the cornerstone of this whole idea. So if you get this, then all of this will just be the same idea again, flushed out in more mathematical terms. So let me stop for a second, make sure everybody understands this funny trick. Is there any way to fix this problem about the barber?
Move the barber out of town.
Move the barber out of town. Right, right. That's a really, really, really good idea. It's an excellent idea. Right, let's move the barber out of town. The barber lives in finite state machine land right now, and we get this funny contradiction. So let's move the barber out to Turing machine land. Here's our barber. He lives out here. And this barber shaves everybody in this town who doesn't shave himself. No contradiction at all. If you shave yourself in this town, then you don't go to the barber. If you don't shave yourself, you go to the barber. And when you go, you got to go through the border and make your way out to Turing machine land. Then you come back and you're nice and cleanly shaved. But there's no issue about what happens, does the barber shave himself or not? Yeah, he can shave himself, right? Because he doesn't live in town. this doesn't apply to him. And he doesn't have to shave. Either way, you can decide it any way you want. So you move the barber out of town. All right, now let's shift over to this analogy with a picture of finite state machines and Turing machines. Instead of barbers shaving themselves, we'll have finite state machines that are accepting strings. Accepting strings is going to be like the shaving, and the barber or the people are going to be like the machines. Okay, that's the analogy. All right, the first thing we need to think about is what's a finite state machine? You all know what they look like, something like this. Done this before. 1, 1, 0, 0. So what's that one? That's a finite state machine that accepts all the binary strings with odd number of zeros. Okay, now, before we talk about all these machines that live in here and whether, something's going to accept them or not, we need a way of encoding these machines as binary strings so we can send them as input into other finite state machines that might decide something about them. So we talked about this once, and there was a way we used to encode this string. I think we started with zeros, and we counted how many states there were, right? So we had 2 states, that was 2 zeros. And then we made a little divider, and we started with the initial state, and we listed the state that it goes to on a 0, that was state number 2. And then the state it goes to on a 1, that was state number 1. Right? And now we went over to the next state. The state it goes to on a 0 is state 1. The state it goes to on a 1 is state 2. And then over here we put 2 1s to show that we're done, and now we're going to list the final states, and the final state is just a single double 0. So that funny little binary string represents this finite state machine. Now, you could represent this finite state machine in a million other ways. This is just one way. There's one method of turning finite state machines into binary strings. There's lots of other methods. Okay, and if you buy this, fine, and if not, let's just say this string represents this finite state machine, regardless of how we came up with it. But now the point is that this finite state machine can start churning on itself. So does this one happen to accept itself or not? Does this person in town shave himself? Does this finite state machine living in finite state machine land accept itself? It doesn't, because this must have an even number of zeros. Okay? So this machine doesn't accept itself, but you could certainly imagine that plenty of other machines I'd write down on the board, when I converted them to their binary strings, they would accept themselves. So some machines in town accept themselves, and some machines in town do not accept themselves. The same way some people shave themselves and some people don't. Okay, questions so far?
But
Yeah,
if you
Teresa.
encode it in a different way, wouldn't it accept itself? And therefore, doesn't everything depend on the encoding?
It completely depends on the encoding. Right. It completely depends on who's the shaving manufacturer in that town. If a different manufacturer walks in, then some people who used to shave themselves all the time actually stop shaving. What if there's a power failure in town? Now, everybody who used to shave themselves with an electric razor doesn't, and
I guess I could say, well, why do we keep going on in this proof, but we don't talk about the encoding as like a deciding factor at one point?
well, you pick the encoding, and then it kind of divides people up into finite state machines that accept and don't accept. But it isn't anything, it's not a function of the language, it's a function of the actual encoding. Some finite state machines will accept themselves and some won't. And it depends how you encode the string. So there's no truth to it. It's somewhat arbitrary whether they do or whether they don't. Is that what you're wondering about? Is it just arbitrary? It is. It's arbitrary whether they do or whether they don't.
No, yeah,
But it's consistently arbitrary. I mean, they will all either accept themselves or not accept themselves according to this one encoding scheme. You can't encode each one differently because that wouldn't make any
I guess
sense.
I feel like if we're doing a proof, then we should have like a list over there of all these assumptions that we made, like, well, encoding is decisive. And sort of what does that mean overall in the proof?
I'm going to convince you that no matter how you do the encoding, as long as it doesn't make any difference how you do the encoding. The proof will go on just the same way. As long as there's some way to turn the machine into a binary string and then run it on itself. It won't matter how you do it. It'll still work the same way. Are there other questions? Well, let's move on, because we're just about up to the point in this proof that it looks like this barber who shaves everyone in town that doesn't shave himself. Let's consider all the finite state machines. and let's consider their encodings, and let's consider whether they accept themselves or not. So some of them do and some of them don't. There's the finite state machines in town that accept themselves and the finite state machines in town that don't accept themselves. All right, so I want to know, is there a finite state machine in town, some big one perhaps, some complicated one, that accepts exactly all the binary strings that represent finite state machines themselves that don't accept themselves? Okay, this is a very fancy finite state machine. It's supposed to take in other finite state machines as input. It takes other people in town in as input, just like the barber takes other people in town into his chair. These finite state machines take other strings in. The other strings represent other finite state machines, and they're supposed to decide, do those finite state machines accept themselves or not? I want this finite state machine to say yes on all the strings that don't accept themselves. Now, that's perfectly reasonable hypothesis to exist, but if that machine existed, I've asked you the question, what does that machine do when I input it to itself? Does it accept itself or not? If it accepts itself, then it's supposed to reject itself, because it's supposed to accept only the finite state machines that don't accept themselves. And if it rejects itself, it's supposed to accept itself, because it's supposed to accept only the ones that don't accept themselves. So it's just like the barber goes into a poof existence and can't exist. This finite state machine that reads all other finite state machines that don't accept themselves, that finite state machine doesn't exist, the same way the barber doesn't exist. So now I've described to you a language that there's no finite state machine for, and I'll write it down. Here's the language. The set of all finite state machines represented by some binary string which do not accept themselves. The set of all people in town who don't shave themselves. There's no barber who shaves all those people. There's no finite state machine who accepts all these finite state machines. It's the same paradox, the same conundrum. So here's the language. All the binary strings representing finite state machines that don't accept themselves, that language has no finite state machine for it. And the proof is just by this logical twist. So let me stop for a second. Teresa, you don't buy it, huh? Seems confusing, huh?
It's like you're setting up a straw man. You know, there's this uncoding thing out there that's sort of, I don't know what to do with. And so it's like the barber. Well, we'll move him out of town, and now it's not a problem anymore. I mean, that's like...
Well, we're going to move this guy out of town, and it won't be a problem anymore.
Okay, I guess...
We'll do that soon. But, you know, you do the encoding. Encode it any way you like.
And you're going to account for both cases, whether it accepts it.
I already did. I mean, it just...
You already have.
Yeah, I mean...
I just need to see where that is.
Yeah, there's nothing that depends on this encoding.
Okay.
I mean, some of the machines accept themselves and some don't, but there's...
Separating them.
Right, you're just separating them into two parts. Yeah. Okay, let's do a little bit, maybe a little visual version of this. A visual way to think of this is to make a table. We just took a finite state machine before and encoded it into binary. So let's use Teresa's method. I don't care what method she uses to encode finite state machines into binary. But whatever method she uses, every finite state machine has some binary encoding. And here's what I'm going to do. I'm going to take all the finite state machines in the world, we'll encode them into Teresa's binary, and then we'll look to see which ones have the smallest binary number, and we'll just order them, all in order, so that the machine that I will now call machine number 1, or machine 0, will be the binary encoding of yours that's the smallest one. And the next one, the one we'll call 1, will be the next smallest binary encoding. And this will be the next smallest binary encoding, and the next one, etc. Okay? So now I'm going to re-encode all these finite state machines to be nicely done in order. That's the smallest one, the second smallest, the third smallest, etc. And I list the strings up here too. And now for every finite state machine, I go ahead and I check whether it accepts all these inputs. Does this machine accept itself? Turns out it does. Does this machine accept the string number 1? No. Does it accept the string 0, 1? No. Does it accept the... Looks like I wrote this twice. Does it accept the string 0, 0? No. Does it accept the string 0, 1? Yeah. Does it accept the string 1, 1? Okay. I'm making these up randomly. I don't know what this finite state machine looks like. It's Teresa's encoding. I don't even know what it is. And it doesn't matter to me. It's some finite state machine. And here's its accepting and rejecting values. It accepts these strings. It rejects these strings. And it goes on forever, accepting and rejecting. And every one of these finite state machines has its own little set of acceptances and rejections. Right? And you can just run through every single input and check. Right. Lots of confused looking faces. How can I help? Okay? Yeah, Joe? What?
The 0, 1 for the FSMs,
Yeah?
is that the entire encoding string, or is that just, you're just using a binary representation?
Here and here and here and here and here?
Is that the actual encoding?
That's the entire encoding of the machine. I re-encoded them. Teresa gave me some complicated encoding, so every machine had whatever, in anywhere from 30 to 180 symbols. So now I just took all those encodings in order, from smallest size to largest size, and I renumbered them. The smallest one I'm calling 0, the second smallest 1, just so that I could number them nice and easy this way. Okay? And that's another way to say that all the finite state machines are countable. You give me a binary number, and then I'll order them as to their size. So I'm going to put down some more 1s and 0s here just to fill up the chart. Okay, and this chart goes on forever. Now, this language we talked about, the set of all finite state machines which do not accept themselves, you can figure out what this language looks like from this chart. Here's a finite state machine. Does it accept itself? It does. Here's a finite state machine. Does it accept itself? It doesn't. I'm going to circle that one. So the finite state machine labeled 1 is a string in this set, a finite state machine that doesn't accept itself. Where's the next one that doesn't? 1, 0, 0, right? I think that one doesn't. Oh.
Well, if you assume that it's an order.
Did I not? Did I? Oh, because I missed you. They're all messed up? That doesn't help? Let me get it right. 0, 1, 0, 0, 0, 1, 1, 0, 1, 1.
You need 0, 1 on the FSM.
Jeez. Can't count in binary, huh? Let me just do it right and count it right in binary. 0, 1, 0, 0, 0. Thank you. 0, 1, 1, 0, 1, 1. There we go. All right. All right, it's just this side that was off. All right. Now we're set. Bye-bye, eraser. All right, so this one doesn't accept itself. What else? This one doesn't. And there might be a lot more. All the strings that have zeros on the diagonal are going to be finite state machines that don't accept themselves. And I want to consider all those strings as a language. So here's what it would look like. It would be 1. It would be 1, 0. And it would be a whole bunch of others. I don't know what they are. I'd have to go down and look. So the set of all these zeros that appear on the diagonal, if I listed them in a big set, that's exactly the set of strings that I guarantee to you have no finite state machine that exists. And it's because of this funny question about what happens to this machine when you run it on itself. So let's see what that question does in terms of this diagram. Let's say Teresa doesn't believe this, and she says, I think there might be a finite state machine that accepts this. So I go, well, where is it? And she says, I don't know, it's down here at the 52nd, entry. Or the 3000th entry. So it's someplace in this chart. So the question is, what happens to this machine when you run it on itself? Go all the way to the diagonal, and a question mark, what's in that spot? Is it a 1 or a 0? If it's a 1, that means it accepts itself. Then what? Is it going to be in the set? Then it shouldn't be, right? But if it accepts itself, if it's really in this set, it's not supposed to be in the set. And if it's not in the set, it's supposed to be in the set. Let's see. The things in the set are all the things with zeros down here. Right? So is this 52 character going to be here or not? I want you guys to think about this, because I've said it, a dozen times in and out, and I want somehow to figure a different way to say it that can help. All these strings are the ones whose diagonal values were zeros. Right? And this is a set of all of those. So what's the paradox about that? The paradox is that if this collection was actually somewhere in this row, if there was a finite state machine to do this collection, then there's going to be 1s exactly underneath all these guys. There's going to be a 1 underneath a 1. There's going to be a 1 underneath the 1, 0. What's there going to be underneath the 52 here? If there was a 1 there, then there was supposed to be a 0, right? There's only 1s underneath the spots that were zeros. Only 1s underneath the spots that you didn't accept yourself. So if there was a 1 in this spot, it's supposed to be a 0. But if there was a 0 in this spot, you were supposed to include it in this list, in which case you're supposed to put a 1 there. There's nothing you can put in this spot that makes sense. If you put a 1 in, it's supposed to be 0. If you put a 0, it's supposed to be 1. And it's the same thing as the barber who shaves everybody in town who doesn't shave himself. All right, Sharon, you're looking kind of quizzical.
Oh, I just had a little flash.
Is it making any sense?
Yeah.
All right, well, this idea is worth understanding at this level, because the next level is very, very similar, but with a teeny little twist. And you really need to get it down here, I think, before you can see it at the next level. It's not too much harder at the next level. It's a teeny bit. So questions about this right now. Here's what we've done. We've proved that there's a set, namely the set of the finite state machines that don't accept themselves. That set has no finite state machine. That set does not exist in this list. You can't find it. It's a pretty wild way of coming up with a language that doesn't have a finite state machine, but there it is. All right. Let me stop. Questions last time.
So does this mean that there are more languages than FSMs?
Oh, yeah. Right. The FSMs are countable. You can list them. Teresa listed them, and then we ordered them. And the languages are the same as the real numbers. They're essentially, every language is an infinite string of zeros and ones. So you can make a one-to-one correspondence, more or less, between languages and real numbers. So yes, languages are uncountable, and programs and finite state machines are countable. Therefore, there's got to be at least one that there's no machine for. And this is the particular one that there is no machine for. Right. Yes, absolutely. What you said is right. All right, let's do the next step. Let's take this barber and, like Donna said, throw him out of town. Bye-bye. What does that correspond to in this analogy? The paradox here was that we assumed there was a finite state machine that accepted all the other finite state machines that don't accept themselves. And we got a paradox. That was troublesome. There is no such finite state machine. We get a contradiction. But maybe there's somebody smarter outside of town that can do it. Maybe there's a Turing machine that can do it. Not even maybe. Go home and write one. Go home and write a program that will accept exactly the finite state machines that don't accept themselves. You should be able to do that. Go home and write a program. I'll give you the finite state machine. I'll give you the input, namely itself. You run the machine on itself, and you tell me, does it accept itself or not? Yes or no? It's completely doable. You could do it tonight. It would take you not too long. It would take you about an hour. Even if you forgot how to use Scheme, it would take you an hour. You could write a Turing machine to solve this problem. That doesn't cause any contradiction. The reason it doesn't is the same reason as when you move the barber out of town, there's no contradiction. Because you don't expect the barber to either shave himself or not shave himself. He's not in the criterion anymore. There can be a Turing machine that decides all these questions, and the question of what happens in the diagonal is not a contradiction, because we don't care whether that Turing machine accepts itself or not. That Turing machine is not under consideration here. We're just saying that Turing machine is smart enough to know the answer for all the finite state machines. He might not know the answer for himself. He's not a finite state machine. He doesn't get included in the criteria. Right? So if he's included there, fine. If he's not, fine. Either way, it's okay. So if you move that guy out of town, there's no problem. And in fact, you can do it. And there is a way to decide all these things. There's no finite state machine that decides it, but there's certainly a Turing machine or a program that decides it. So this is not hard to decide, just that a finite state machine is too stupid to do it. It's too self-referential. All right, questions about that? Well, there are things that Turing machines can't do. And what's going to cause us trouble is we sent the Turing machine out of town. The barber went out of town, became a Turing machine. So now what we're going to do is open up the gates here, you know. Everybody can live wherever they want. And now let's talk about the Turing machine that shaves everybody in town that doesn't shave himself. And that Turing machine is not going to be around. That Turing machine is going to go poof into oblivion. But here there's a real strange subtlety. And the subtlety will come up in making this diagram. And there's a little bit of a subtlety, and that's why I want to make sure you get this diagram without the subtlety. The thing about this diagram is that we can really fill it out. Give me a finite state machine. Give me an input. I can tell you 1, 0, 1, 0. I can just execute it and tell you what happens. And I can do it for every single one. And I get this funny contradiction. If we try to do the same trick for Turing machines, something happens along the way, and we have to kind of zigzag and do a tricky logic trick. But when we're all done, the same result will occur. The Turing machine that accepts all other Turing machines that don't accept themselves, that doesn't exist at all. And it's going to imply that the halting problem is undecidable. So that's where we're heading. And we're going to start that in 30 seconds. Are there questions about this? Yeah?
Can you have a meaningful machine which has a totally random response to whether it accepts itself or not?
It's a really good question. I'm hesitating not because
Digression.
it's a good question. It's not even a digression. A Turing machine, as it's defined, is like a program in the sense that there is no randomness to what it does. If you give it an input, you can watch what it does. And there's no question that at some point it will either infinite loop, or it will accept, or it will reject on a given input. However, there are versions of Turing machines that people talk about in order to simulate random computation, where the Turing machine is allowed to like spin a die or pick a random number in the middle of its computation to try to model the idea of randomness. And we're not talking about those Turing machines at all here. And that is a long digression and a very interesting topic. But here we're assuming that every Turing machine is deterministic in the sense that you know what it's going to do at every step. Okay. Other questions? Okay, let's move on to the next step then. We move from barbers to finite state machines, and now we're moving up to Turing machines. Okay, so here's what I'm going to do. I'm going to make this list of strings again. 0. You know what? So I don't mess up this list, how about if I just number the strings? No more binary. I'll mess it up in binary. 1, 2, 3. It's like the Mighty Python movie. You shall count to 3, you shall not count to 4, you shall count to 3. You shall count to 2 only on the way to 3, and 1, 2, 4. 3, sir. All right, these are Turing machines. These are inputs. Same trick as before. Turing machines, as you know, are funny, these pictures with these arrows. There's a way to encode them in binary, just like there's a way to encode finite state machines in binary. Pick any way you like, and whichever way you like, give me the one that's the smallest, and I will call that Turing machine 0. Give me the one that's the next smallest in binary, I'll call that Turing machine 1. So these are the ordered Turing machines according to whatever encoding you like, from smallest to largest. And these are the identical strings as inputs. And these Turing machines, you could run them on every single input to see whether they accept the inputs, reject them, or run forever, I guess. That's the thing about Turing machines. They don't just say yes or no. They might not say anything. They might just work and work and work. So if we try to do this trick with Turing machines, we have this immediate problem that we can't fill this table in necessarily. If I run it on itself, what if it just runs and runs? I don't even know whether to put a 0 or 1 in there. So you might think, oh, well, great. I can't even make this table, so maybe I won't have this contradiction. Well, that's fine, but nobody's satisfied with that. So here's the subtlety to get around it. We're going to assume, and it's not a reasonable assumption, but we're going to prove that it's not a reasonable assumption as we go. We're going to assume, perhaps unreasonably, that there is a way for us to put in 0s and 1s here. And how are we going to assume that? By assuming that there's some program somewhere where if I give it a Turing machine and I give it an input, it tells me whether that Turing machine accepts that input. I've got a magic halting machine tester. So here's my magic halting algorithm. I'm assuming it exists. It doesn't really. Okay, but I'm assuming it exists, and in continuing here, I'm going to get a contradiction which will imply that this assumption is completely erroneous. But I can't prove that it's erroneous until I actually make the assumption and get you some weird contradiction. The weird contradiction is going to be the barber. And then I'm going to back up, and the only assumption I will have made that's questionable will be this one, that this exists. So let me tell you what this is that exists. The magic halting algorithm. I give it a Turing machine and a string. I give it a Turing machine and a string. It tells me, it outputs, does M accept X? It tells me yes or no. Does M accept X? If it tells me yes, I know the answer is yes, it accepts X. If it tells me no, I know that either it rejects it or it infinite loops. I don't care which one, I know it doesn't accept it. It's going to tell me yes or no if I give it an M and an X. And if I got something like this, then I can fill in this table. Keep in mind that we did have something like this for finite state machines. There, it's not magic. There is a halting algorithm for finite state machines. You can write it yourself. Put in a finite state machine M. Does M accept a string X? Yeah, go check. It's just that we don't have that necessarily for programs. Nobody knows how to do it. So let's assume we do have it. I'm going to show you we got a weird contradiction. So let's fill this table in. It's got 0s and 1s just like before. All right, so there's a few entries. I just made them up. Representing whether Turing machine labeled this number accepts a string labeled this number. You can also see if these machines accept themselves. 0, 0 accepts itself. 1 accepts itself. 2 accepts itself. Oh, they all accept themselves. All right. There's one that doesn't accept itself. Well, fine. All right, now I can fill this table in. And just like before, I am now going to come up with a set that can't possibly exist. And what is that set? I know I've made an assumption in order to do this. We'll go back and fix that assumption in a minute. But what's the set that can exist, assuming I have this diagram? The set of all things with 0s in the diagonal, or the set of all Turing machines that do not accept themselves. That means either they reject themselves or they infinite loop. That's a set that doesn't exist. Just like it didn't in the other two cases, just like the barber didn't exist. Yeah, Joe?
How do you know that the input 0, right, string length 0, is the same string that's generated by the Turing machine 0 when you encode it? Right? That's how you know it doesn't accept itself, because that string 0 has to be the encoding of the Turing machine 0 so that they match up and give you either a 1 or a 0 in that diagonalization. Is that right?
I'm not sure what you mean exactly. These numbers represent Turing machines.
Right.
So this is some Turing machine. I don't know what it is. Maybe it's the one that accepts 0 to the n, 1 to the n, 0 to the n.
Okay.
And this is the string 0. So if this Turing machine really is the one that accepts 0 to the n, 1 to the n, 0 to the n, then there would be a 0 here. It doesn't accept 0.
Right.
And it doesn't accept 1. And it doesn't accept 1, 0. It wouldn't be up until like 1, 0, 1 until you'd actually get an acceptance there. Does that?
Okay, that's okay.
That help?
Assuming that's correct then, 0, you would have it. How do you know that it doesn't accept itself though, if it's from the input string? Because you're looking at the diagonalization.
How do I know what doesn't accept
You're
itself?
saying a Turing machine doesn't accept itself.
Some of them do, some of them don't.
Right.
Right. I just run it on the encoding that represents it, and I see whether it accepts itself or not.
But that encoding wouldn't necessarily be
Wouldn't
in the
line up.
same spot. Okay, the encoding for the Turing machine 0, right, is some 10-character string.
No, it's just 0. I re-encoded them. Teresa made her own encoding, and I relabeled them all. So now they have a new encoding in order, so I could just list them in order and not miss any. So let's say originally this was encoded with a number that was 36. Maybe these were the original encodings: 36, 42, 53, 98. So rather than list these and have to deal with all the gaps that might have appeared, I just say, well, let me take Teresa's encoding and redo it. So now that the one that was the smallest I call 0. I just re-encoded them all. If you want to figure out which one it is, you can just go look it up. So how do you know? You just know. I mean, I just defined it that way. 0 is that Turing
I
machine.
know, but in order to take string 36, you
It's not string 36. This is string 0 now.
I understand
That Turing machine's not 36 anymore.
I think what Joe's trying to confirm
Mm-hmm.
is that you're defining the input 0 is now equivalent to your encoding for Turing machine 0.
They're exactly the same.
Yeah.
Okay.
They're
I think that's all.
okay. Well, Heather understands the question completely. Yeah, so yes, they're exactly the same. This Turing machine looks like a 0, and it's looking at a 0. This Turing machine looks like a 1, and it's looking at a 1. Yeah, they're the same. They're exactly the same. Okay. So we go through this procedure. We got this whole stuff written out. And just like before, we have this strange set that can exist, and I'll write it out. Here's the set that can't possibly exist. Ironclad logic can't possibly exist, assuming I can make this table. It's the set of all Turing machines that do not accept themselves. You cannot find this language in this list. It doesn't exist anywhere. If it did exist, it would contradict the diagonal entry. So it doesn't exist.
Time to move out of town.
No, we're staying in town this time. Right, there's no more towns to go to. That's the thing. That when you're at the Turing machine level, you can't go out of town. If you go out of town, you know, you hit the border. Go back in town. It's like the Twilight Zone. You know, you leave you look around, you're still in the same town. You go out of the town, you're still there. I mean, that's.
Can't someone discover a new town eventually?
I guess there is this idea of an oracle. Right. Well, here's the thing. You see this machine that can't possibly exist? You all agree it can't possibly exist? All right. Assuming that we could make this chart. Remember we assumed that this existed? This funny assumption. I'm going to convince you now that, I mean, we haven't gotten any contradiction. So what if this doesn't exist? You all agree this doesn't exist. Fine. How does that relate to my assumption that I made? I'm going to show you that the fact that this doesn't exist is in direct contradiction to this assumption. And that means this assumption is bogus. This assumption means I can give you guys an m and an x. You can go home to your halting algorithm and tell me whether m accepts x. You'll answer yes or no to this question. You did. You let me do this, right? If you can do this, I can tell you to go into your program, and every place it says yes, change that to a no. And every place it says print no, change that to a yes. Okay? You can all do that. You go home and do it, change the algorithm. This is the recursive algorithm. This is a legitimate algorithm that says yes or no on every one of these inputs. I say switch your answers around. Do the complement trick. Make your yeses no's and your no's yeses. Then what set does your new machine that I told you to switch around, what does it accept? It says yes to all the Turing machines that don't accept themselves. So the existence of this assumption implies that there really is a Turing machine that says yes to all the Turing machines that don't accept themselves. It's just the toggle of your Turing machine. But we just convinced ourselves that that Turing machine that accepts all the others that don't accept themselves, that doesn't exist. But it would exist if we had this thing around. So it's a contradiction, this assumption. This assumption contradicts the fact that this doesn't exist. So I'm going to write this down a little more carefully. This doesn't exist. That's by the Barber argument. And the fact that that doesn't exist, this assumption implies, let's call this, I'll give this a name. I'll call it weird set. The weird set doesn't exist, and this algorithm implies that the weird set does exist. Why does it imply that the weird set does exist? Because just take whatever algorithm you use here and switch the yeses for nos. So this assumption implies that weird does exist. All my logic implies that weird doesn't exist. So this assumption's got to be wrong. That means there's no algorithm at all that tells me whether M accepts X. That means that this problem is undecidable. So that's the end of the proof, and that's the proof. We have our first kind of like original sin here. This is the first problem that you just can't do. No way to do it. And it's really, really based on this little trick. So let me stop for a second. This is exactly actually the way our book does it, in principle. There's other ways to prove this, all essentially equivalent. They might not seem equivalent to you at first reading, but they really are. And our book does it just this way. It assumes the existence of this, implies the construction of this table, derives that this set can't exist if this table exists, and then says, but this implies that that set does exist, so this can't ever be a reasonable assumption. Therefore, there's no algorithm that is magic that does the halting problem. It doesn't exist. So this is different than the finite state machine level. Here we have to make an assumption of something existing and then showing that it didn't exist. Before, there really was a Turing machine that did it, and all we got as a result was that there was no finite state machine. But here we got that there was no Turing machine by this extra little trick. Let me stop for a couple minutes and let you ponder this and ask some questions. Let's look at that again. This is a magic halting algorithm. I give you a Turing machine and an input, and you tell me, does that Turing machine accept it? You say yes if it does, and you say no if it doesn't. I don't know how you do it, but you've got it. And I say, go back to your program, and every place where there's a line that says, yes, change that to no. And every place there's a line that says no, change that to yes. So now your Turing machine is going to say yes every single time the other one used to say no. Yeah.
Now this is because of the fact that we've defined computability to be the things that Turing machines can do, and therefore for an algorithm to exist, it has to be computable by a Turing machine.
Yes.
So conceivably, if we were to broaden our notion of computability outside of that realm, then this might not be a problem.
That this wouldn't contradict that.
It would be akin to
moving out of town again. Right. So Neil asked before, can you move out of town again? And Chris is asking this in a more rigorous way. Can you go ahead and broaden our sense of computation to go beyond a Turing machine? Sure, a Turing machine seems to model computation, but it doesn't seem to model the way I decided who I was going to marry, for example. I don't think anybody was going to write a Turing machine to do that and consistently print yes or no to successful marriages. There seems to be some quantum emotional biological response, and everybody manages to pick the right mate. No. The point is, it is possible that there are levels of computation above Turing machines. There can be quantum computers, perhaps. There could certainly be computers that work on some randomness or some kind of level that's beyond the deterministic, step-by-step mechanistic level that we assume Turing machines are. And if that was the case, then it is possible that one of those computers could really answer this question and then wouldn't have an issue with contradicting itself because it wouldn't be in the group under consideration. That's possible. Yeah.
Which, of course, just expands the problem.
It just expands the problem to the next level, right?
Yeah, I guess that's my next question. Is there any hope ever?
No, there's no hope. No, there's no hope. No, we have fundamentally cannot compute things, period. You come up with your model of computation, and there will be questions about that model that model is not powerful enough to compute. It's always the case. That's what diagonalization says. It says that these machines are not smart enough to be completely self-aware. And that's just the way it is.
And any machine that we could construct that is completely aware about
wouldn't be aware about its own members completely. Right. Right. And I think we're just computers, and we count too. We're also not completely self-aware. It goes the same way. But not everybody thinks so. Or do I?
Why doesn't it work at one layer down on the FSMs, this magic algorithm? Why can't you do that?
You can do this. This magic halting algorithm exists. I mean, there is a Turing machine that will say yes or no whether a finite state machine accepts itself. There really is. But that Turing machine is outside of the realm of finite state machines, so it doesn't have to accept itself or not accept itself according to that Barber criterion. But there is no finite state machine that can do that for finite state machines, and that is exactly the same reasoning. In fact, the only reason we got past this subtlety with finite state machines is because I told you we created this table using a Turing machine for finite state machines. If finite state machines were the limit of our computation, you would have stopped me right there and you would say, well, how do I make this table? Finite state machines can't make that table. Or can they? And at that point, the argument would have been identical to what we just did here. The only reason the argument is a little different is because we get to the frontier of what we think is computation. And the question of just coming up with this table is the same as the question that we're trying to show can't be done. So you get this kind of backhanded proof. Yeah, Joe?
Why can't you move the machine inside the finite state machine? Make it a finite state machine to read all Turing machines, since it's like a separate town.
It's inside.
You mean the Turing machine that accepts finite state machines that don't accept themselves? Why don't I move it inside the town?
The Turing machine that accepts all Turing machines that don't accept themselves.
Well, there isn't any Turing machine that does it. Right.
But I mean, if you
Yeah.
moved it to the finite state machine level.
But all finite state machines are also Turing machines.
Okay.
Okay. I'm not sure I understand the question or the answer, but I know there was communication. It's my happiest moment as a teacher when two people seem to communicate, understand the material better than before, and I have no idea why. That's the way. Good. Whew. All right. More questions about this?
So does this correspond to the fact that any mathematical axiomatic theory, there will be questions which you can't answer?
It's very similar. It's not exactly the same proof, and the proof for that is different, but the notion behind it is similar, and it's for the same reason. Yes. It's very similar.
Which proof came first?
The one that Sham just said, yes, that came first, I'm pretty sure. Yes. That every mathematical system that's powerful enough to describe the rules of arithmetic has statements that are true, which cannot be proved one way or another within the system. That is, look, if this is a little confusing, I think that's more confusing. I really think that that's harder to get. I don't know. I think it's harder. This is, maybe I just thought about this more. All right. There's a lot we did today, but there's also a lot we didn't do. Let me give you a little heads up on where we're going. We've been going for a while. I'm not going to do anything more complicated. I'm just going to tell you what we're going to do next time. We finally proved that we have a legitimate problem that's undecidable. If I give you a machine and a string, and I say, does that machine accept that string? No way to do it. No way. That problem is not recursive. It's not decidable. Its complement, the set of things that you don't accept themselves, that's not even recursively enumerable. That's this thing. So this is not even recursively enumerable. And its complement, the set that do accept itself, that's undecidable, but it is recursively enumerable. The set of things that do accept, the machine accepts the string, you can just simulate it. And if it accepts it, sooner or later you'll get the answer yes. So you can get the answer yes when the answer is yes. You just won't get the answer no when the answer is no. But this one, where you switch the thing around to its complement, this one you can't even say yes to. This one is not recursively enumerable. So we've got an example of our first set that's undecidable. What we want to do from here is kind of move it to problems that are a little more practical. Take this thing, which is undecidable, and reduce it to other problems. So we're going to do a few reductions of that sort. And the reduction that we'd really love to do, but it's just too tedious, and I'm not going to do it, it's to show that this halting Turing machine problem reduces to PCP. The PCP problem, you guys remember that problem? You're given a set of strings like this, like 0, 1, 0, 1, 1, 1, 0, 1, 0, 1, 0, and then maybe 1, 0, 1, 1, 1, 1. And the question is, can you make a sequence of these in some order where when you concatenate it together, you get the same string as the same sequence on the other side? Yes or no? Can you do it or not? And that problem, I told you, was undecidable. Do you know how to prove that's undecidable? It's a tedious proof, but at least I'll give you the just most general picture, just to give you a general sense. Here's how you show that that's undecidable. You show that if somebody could solve this problem in general, if somebody could take a long list of binary strings and tell you whether you could put them together in such a way so that the left side was the same as the right side, if somebody could do that, let's say you guys can do it. You know a way. It's the secret ADU PCP algorithm. It sits in the back of the room. If you knew a way, then I could figure out how to solve the halting problem. Well, how would I do that? Well, presumably, the halting problem gives me an M and an X, a machine and an input string. Somehow, I would take that machine and the input string and construct a long list of zeros and ones strings and hand them to you. And I'd say, go run this on the PCP machine. And you'd run it, you'd tell me yes or no, and presumably, I would construct it in such a careful way so that if you told me yes, this machine would accept X. And if you told me no, this machine would not accept X. I would connect the machine and X to a list of strings so that the solution of those strings on the PCP was the same exact answer to the solution to whether M accepted X. Now, how do you do that? It's such a mess. You have to take the machine, you have to take the input, and you've got to decide exactly on what those strings should be. Now, intuitively, do you know what those strings end up being? They end up being pieces of a configuration of a computation of the machine on this string. Remember what a configuration is? It's a picture of the machine. And then if you go to the next step, you get another configuration, another picture of the machine. If there's a way to connect those together, each string might represent a possible configuration. They can connect together if one can get to the other. If you can connect those together so that this side equals this side, then there turns out to be a way to get to an accepting state on this string using this machine. And if there's no way to do it, then there's no way. You really carefully make those strings to correspond to the machine and the string. Now, the how and the details is a little gruesome. And it's described in very detail in the book. I mean, he really goes through it, gives you the big picture and the details. But I don't know, I just don't think it's really worth doing as a regular lecture. It's just tedious, and I don't think you'll get it sitting through it in a lecture. If you stared at it for 5 or 6 hours and then I went through it, you'd probably get it. But then you'd probably get it even if I wouldn't go through it. So I'm not sure how much going through this in a lecture really helps the details. So I'm not sure I want to do it. But maybe I'll do a little piece of it or something. There is this little stage. In this reduction from here to here, there's actually a two-stage problem. You actually reduce it to a problem that's a little bit simpler than PCP, or seems like it's simpler. It's a problem just like PCP, but you have to start with a first string in your sequence. Okay, if I give you PCP and ask the same question, but I also insist that you have to start with the first string. That's what MPCP is. Now, why is that closer to the halting problem? Why do you think you'll have an easier time taking a machine and a string and connecting it to a problem where you have to start with the first string than just a problem where you could start anywhere?
Because you do have to start in a particular start state.
Because you have to start in the start state, in the initial configuration. And the initial configuration ends up being somewhat akin to this first string. So I would love to be able to deal with my target being something where I have to start with the first string. So in order to do that, you're working with a different problem. And maybe that problem is hard, but it seems like it might be easier than the general PCP. So I can show you tomorrow, and it's kind of an easy proof, that if you can solve that problem where you start with the first string all the time, then you could solve the general problem too. That it's actually no easier. It's just as hard as the general problem. And that gives the author the ability to narrow his target to something more attainable. And that's really what the author does. So we can show this reduction. We can show the reductions from PCP to all the grammar questions. And we're also going to show reductions from this halting problem to all these other interesting things you'd like to know about Turing machines. Anything you want to know about Turing machine, forget it. Here's a Turing machine. Does it accept a regular language? In other words, is the language it accepts the same as some finite state machine? Yes or no? No way to decide. Here's a Turing machine. Does it accept absolutely nothing? Is its language empty? No way to decide. Does it accept everything? No way to decide. All those questions that are undecidable are reductions directly from the halting problem. If you could solve any of them, you could determine whether a machine halts on a given input. And I'm going to explain that connection. That connection is not obvious, and your brains are too full for one day to do it. But that's what we'll do yesterday. We'll talk about reduction. Yesterday? I'm losing it. Well, that's what we'll do tomorrow. We'll talk about reductions from the halting problem and from MPCP to PCP. When we're done with reductions, we're shifting over to computational complexity, talking about P, NP, P-space, and hierarchies of how long it takes to really do things that you can do. No more stuff about things you can't do after that. All right, let's quit.